We are now going to proceed to Theorem 10.8, the measure of an inscribed angle. Theorem 10.8 reads, if an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc. So that here we have a picture of a circle. We have points A, B, and D that lie on the circle, and we have angle ADB that is inscribed in the circle. Remember, an inscribed angle means that the angle itself, the vertex of the angle itself, lies on the circle. So here ADB, the point D lies on the circle. And the theorem tells us that the measure of the angle ADB is 1/2 of the measure of arc AB. And remember, the measure of arc AB is the same as the measure of the central angle ACB, where C is the center of the circle. So basically this theorem tells us that ADB is 1/2 of the measure of ACB. I've just redrawn the circle here, and you can see I've changed the lettering just a bit. So we have an inscribed angle in a circle. The angle is ABC, where B is on the circle, and the angle ABC is an inscribed angle. And we need to prove that ABC is 1/2 of the measure of the arc AC. It's going to take us quite a bit of work to prove this theorem, and we're going to have to prove it in stages. So I'm first going to prove it for a special case of inscribed angle, and then I will be able to generalize to all inscribed angles. So we will start instead by looking at a slightly easier problem. In this case, we're looking at angle ABD. This is different than angle ABC because in this case, BD is a diameter. Okay, so this is an inscribed angle, ABD, but an inscribed angle where one of the sides of the angle is a diameter. Well, how does that make this problem a little bit easier? Well, it makes the problem easier in the following way. What we can do is we can draw from the center O to point A a radius, and we know that all radii in a circle are equal, so we have AO is equal to BO. We have the two radii of the circle are equal. That makes ABO an isosceles triangle, which means that angle A is equal to angle B. That's true for all isosceles triangles. But we should also note that angle AOD is an external angle of the triangle AOB. So we could write an E here standing for external angle, and that would be this angle here. Now, we know from our theorems on triangles that an external angle, let's say angle E, is equal to the sum of the interior angles, which would be angle A plus angle B. Angle A plus angle B. I'm having a little problem with the visual scope of this, where I sort of am writing a little bit outside what you can see in the video there. So what I'm going to do is I'm going to try to compress and not use the angle sign so I can get the rest of this within the scope of what you can see in the video. So basically, angle E equals A plus B. But we also have that A equals B. Therefore, we have that angle E equals angle B plus B. We just replaced A with B because we know A equals B. Or that's another way of saying E equals 2 times angle B. Well, if angle E equals 2 times angle B, we know that angle E, which is the external angle, also happens to be a central angle, AOD, which is the measure of arc AD. So where we have angle E, we could also put the measure of arc AD. So let's write down here the measure of arc AD. Well, now we know that equals 2 times B. But B is the inscribed angle ABD. So we have just proven that, now all we need to do is divide both sides of this by 2. We have just proven that 1/2 times the measure of arc AD equals angle B. And that was what we needed to prove, that the inscribed angle B was 1/2 of its intercepted, the inscribed angle B is 1/2 of the arc that it intercepts on the circle, or B equals 1/2 times the measure of AD. So now we've been able to prove this theorem for an inscribed angle where the diameter, where one of the sides of the angle is a diameter. So now let's return to our original problem. We had angle ABC as our inscribed angle, where AB and BC aren't necessarily diameters, but we can draw the diameter BD. And what we do know is that for ABD, this theorem is true, and for CBD, the inscribed angle theorem is true, because both of those angles share a side that is a diameter. So in other words, we know that for angle ABD, we have that equal to 1/2 the measure of arc AD. Oops. Okay, let's just redraw that again. That's 1/2 times the measure of arc AD. Okay, and that's because ABD has a diameter as a side. We also know that for CBD, we have angle CBD is equal to 1/2 times the measure of arc CD. That being true because CBD has one of its sides as a diameter. So in order to actually come up with the statement for angle ABC, it's at this point fairly easy once we notice that angle ABC is actually angle ABD minus angle CBD. So we could actually take these two as an equation, these two equations, and subtract one from the other. The left side will give us angle ABD minus angle CBD, which we, by the way, know is angle that's equal to angle ABC, is equal to 1/2, I'm just going to draw it with the new lines, 1/2 times the measure of arc AD minus the measure of arc CD. Let me just move that over a wee bit so that you can see that, just in case it gets clipped off at the edge. So now what we know is that the measure of angle ABC, consolidating our terms, equals 1/2 times the measure of arc AD minus the measure of arc CD. But AD minus CD leaves the measure of arc AC. So what we have is angle ABC, which is the inscribed angle, is equal to 1/2 times the measure of arc AC. And this was what we originally were setting out to prove. So that by being able to prove that this is true for inscribed angles whose sides are diameter, by subtracting two such inscribed angles, we can come up with any arbitrary inscribed angle, and we can prove that any such arbitrary inscribed angle is equal to half of the measure of its intercepted arc.